Most people know that the area of a circle is pi r squared, that is, the radius of a circle squared times by this circle constant pi. But why is the area of a circle pi r squared? So I'm going to use some intuitive methods to show why the area of a circle is pi r squared, and then perhaps express it in a more mathematical way as well. If you don't have any knowledge of calculus, then by all means skip over the more mathematical bits and just look at the intuitive bits, which are perfectly fine for trying to understand why the area of a circle is pi r squared. So the way to do it is to express the area of a circle in terms of shapes that we understand. So I've cut up these circles into these little sectors, and I'm sticking them together in this particular way, and eventually it'll make a shape that looks a little bit like a parallelogram. Obviously it's not a perfect parallelogram because you've got these curvy bits on the top and the bottom, but if you see that the second circle I'm using smaller pieces, so the curves aren't as prominent with the smaller pieces. Now you can imagine if I took smaller and smaller pieces, i.e. more and more of these sectors, it'll look more and more like a parallelogram. And that's essentially how we're going to do it. We're going to imagine what would happen if we took the infinitesimally small sectors, and you'll see that the top shape and the bottom shape look like they roughly have the same area, which of course they should do because they were taken from two identical circles. So back to the usual format. So you can see that again I have this circle which, like in the animation shown before, we're cut into all these little sectors, and you can arrange these sectors so it looks like the parallelogram, which again we discussed. Now you have to imagine that this is a perfect parallelogram, and this would be the case if you took the tiniest possible segments that you could take, an infinitesimally small segment, it would be a perfect parallelogram. So what are the dimensions of this parallelogram? Well, you can see that these little curved bits are obviously these little edges here. So all of these together is the circumference of the circle, because if you go along here you'll eventually go all the way around the circle, which is the circumference. So all of these little bits and all of these little bits eventually add up to be the circumference. So of course this side is the circumference divided by 2, because there's two sides. What's this side? Well, you can see that each segment goes from the circumference, from the perimeter of the circle, right into the centre. So obviously this is a radius. So each one of these straight lines is a radius. So this outer straight line has to be a radius as well. Now, the area of a parallelogram is the same as the area of a rectangle, and there's a diagram here to show why. You've got a rectangle here we know the area of a rectangle is this side times this side. And it's the same as the area of this parallelogram, because you're losing this blue bit, but you're gaining this red bit, so the areas cancel out. So the area of a rectangle is the same as the area of a parallelogram. So to find the area of the circle, we simply have to multiply the circumference divided by 2 and the radius. Okay, so the area is equal to the circumference divided by 2 multiplied by the radius. Now, the circumference we know is defined as 2 pi multiplied by r, and this is just the definition of the circle constant pi. We know that the relationship between the radius of a circle and its circumference is given in terms of 2 pi. So this is equal to 2 pi over the 2, and the 2's cancel out, so we get pi r squared, which again is what we would expect to get. So this is sort of calculus in disguise, because if you know a little bit more about maths, you'll know that to calculate the area of a circle you can use calculus, and this is essentially this method. It works because you're taking a limit. In this case, the limit as the area of these sectors go to 0, and you can intuitively see why that would be. If you want to express it in a more mathematical form, and I'll go through it a little bit here. So we've got the circle here, and this is one particular sector. We'll call the angle theta, and I've cut this triangle out here because what I want you to understand is that if the sector is really, really tiny, then you can't see the curvature of the circle, and this is the whole point. This curvature here will be very tiny if the sector is very, very small. And note that the size of the circle doesn't matter, because you can describe a circle completely in terms of its radius. If you know the radius of a circle, you can know everything about the circle, because a circle is just defined as points that are equidistant from a particular point. So all you need to know is the radius. So this triangle is what these sectors would look like if they were really, really tiny, because you wouldn't be able to see this curvature. So we need to do some geometry to work out some bits of this triangle. So if we call this side alpha and this side alpha as well, of course this is going to end up being the radius, and then this side, this little bit here, as beta. This you can see that this is made of two right-angled triangles. So the Pythagorean theorem says that alpha squared plus beta squared plus this thing squared is equal to alpha squared, the hypotenuse. So this side has to be alpha squared minus beta squared. Okay, so what is the area of this triangle? Well, it's this side, beta, multiplied by this side, which is square root of alpha squared minus beta squared by Pythagorean theorem, divided by 2 to get this bit, but we also have to times by 2 again because there's two right-angled triangles. So in other words, the area of this triangle, which is an infinitely small sector, or this is going to be, is beta multiplied by the square root of alpha squared minus beta squared. Okay, so this is not too useful, because what the hell's beta? I mean, there's no useful quantity for beta here. So we need to express beta in terms of alpha, and we can do that using trigonometry. So of course, this angle is going to be theta over 2, because we define this angle here to be theta. So we've cut this big triangle in half, so this angle is going to be theta over 2. By the definition of sine, of course, beta over alpha, that's the opposite side over the hypotenuse, is going to be the sine of this little angle here, the sine of theta over 2. So we've got an expression, so I mean, just take alpha onto the side, and we've got an expression for beta in terms of alpha. So substitute this alpha sine theta over 2 to all the betas, and we get this. And this can be factorised because there's alpha squared here and alpha squared here, so we take alpha squared out. We've got alpha squared in the brackets 1, because alpha squared times 1, minus sine squared of theta over 2. And of course we can take alpha squared out of this, because the square root of alpha squared is just going to be alpha, so there's going to be an alpha that comes outside, which hits this alpha and makes alpha squared. And then inside the square root we've got 1 minus sine squared of theta over 2, but we know that 1 minus sine squared of anything is equal to cosine squared of that thing. I mean, that's a common trigonometric called the Pythagorean identity. So we know that 1 minus sine squared of theta over 2 is equal to cosine squared of theta over 2, and we square root that and we get cosine of theta over 2, so we get this thing. But we know from the double angle formula that sine of 2a, sine a cosine a is equal to a half sine of 2a. So of course you just substitute the theta over 2 for being a, and you end up with this. This is just a double angle formula. There's nothing, I mean, you feel free to look that up. I think I referred to it in previous videos. I'm not going to derive it in this one. This is just trigonometry here. But so using the double angle formula, we can convert this into a half alpha squared sine theta. You've probably seen this before. This is just calculating the area of a triangle in terms of side lengths and angles. So we know the area of this triangle as being a half alpha squared sine theta. And then this is where the calculus comes in. So what happened here was just geometry, but it was actually calculus in disguise, because we were taking a limit as the area tended to 0. So it would be at this point where, to formalise it, you would use some calculus. So what we want is the area. We want to sum up all these areas here, okay? Sum up all these segments, and we know that the area of each individual segment is a half times alpha squared, which is going to be the radius. Notice that remember that these triangles are just tiny segments. So alpha is going to be the radius, and we've got the sine of theta, which of course theta is going to be tiny because these segments are small, so theta is going to be tiny. So all we need to do to calculate the area of the circle is add up all of the areas of these sectors. So we need to add this sector, add another sector, and add all of them. And of course there's going to be loads because theta is going to be so tiny. That the only way we can approximate this sector as a triangle is provided that theta is very, very small. So what we need to do is take the sum. So this is my index I, so I'm taking the sum over I of all of these areas. So of course r squared is not going to change. So it's always and then sine of each individual angle. So so we've got this first one here, second one here, third one here. They're all going to be the same, but this index is just to keep track of them all. I've got to sum all up an infinite amount of these essentially. Of course, we're taking a limit here. We're taking the limit as theta tends towards 0. So actually this sum becomes an integral. A discrete sum becomes an integral in the limit, where the thing that you're summing becomes very, very small. So we actually get an integral. And when we have an integral, we know an integral is just a continuous sum. We know where we're summing from because of the definition of angles in terms of radians. We're summing from 0 to 2 pi. Remember, there are 2 pi radians in a circle, so this is just the definition of an angle. In other words, this arc length here is equal to r, the radius, multiplied by the angle, and there's 2 pi of these radiuses, 2 pi radiuses, or radians, in the entire circle. So this is by the definition of the angle. We need 2 pi of these radians. So we've got a half r square, which stays the same, and then we're summing over all these sine thetas. But remember that we can use the small angle approximation, which I've alluded to in previous videos, and that's in the limit that sine theta becomes very, very small. Sine theta behaves a little bit like theta, and you can check that if you take the sine of a tiny, tiny angle, it's basically the same as the angle itself. And you can look at this by drawing a straight line on a sine wave curve, and you'll see that the line y equals x is very, very close to the curve, provided that the angles are tiny. So we can, because we're taking the limit of a small angle anyway, we can immediately call sine theta just theta. That's fine. All we have to do now is evaluate the integral, and if you know how to do calculus, then you'll know how to evaluate this integral. If you don't, then that's fine. But you can see that using this mathematical formalism, we also arrive at pi r squared. Essentially, this method and this sort of geometric way of thinking about it are identical. It's just that this is sort of a little bit more formal. But these are identical methods, one using calculus, one using intuition. Again, I'm going to go through a second method. I think Wikipedia calls this one the onion method. But this one's perhaps even more intuitive to understand in terms of the calculus, but maybe not so for the geometric picture. So there's not going to be any animation here because it was tedious enough to make the first one. But now you can see you can divide a circle up into all of these little strips that you can pull out, and you'll notice that provided that the width of the strips is very small, again we've got to keep the width of the strips small, it's going to be like a rectangle. It's not going to be exactly a rectangle, but provided that the width of the strips is small, it's almost going to be a rectangle. So if I pull each of these strips out, we end up with we start off with a strip that has the length of the entire circumference of the circle, obviously, and then as we go in, the strips are going to get smaller and smaller and smaller and smaller until eventually we hit the centre. Of course, these will only be rectangles, like I say, if the strips are really, really thin. So this is obviously an over-exaggeration. There's going to be some curvature here. But of course, if the strips are really thin, then this doesn't matter. But you can see that in the event that you have an infinite number of these strips and they're really small, then you're going to have a triangle here. So we know how to calculate the area of a triangle. So you can see that a triangle, this triangle is just half the rectangle. So this rectangle here, this big rectangle here, is just c multiplied by r. But of course, it's a triangle that occupies half of the area of the big rectangle. And you can see that in this square you've got an empty bit here and a filled bit here, and then in this square you've got an empty bit here and a filled bit here. So of course it's the area of this rectangle divided by 2. In other words, CR divided by 2. And using the definition of the circle constant pi, we can express the circumference in terms of 2 pi r, which is 2 pi r squared divided by 2, and again we yield the area of the circle being pi r squared. Okay, I'll go through the mathematical way of doing it. So mathematically, this one looks somewhat less hideous, but maybe it's a little bit more counterintuitive. So I'm going to start in the middle this time because it's probably easier to think about it that way. So what we need to do is imagine these are rectangles because the strips are so thin. So what we need to do is sum up all these infinitely thin rectangles all the way from starting right in the middle all the way out. So we need to add them all up. So what's the area of each individual strip to begin with? And remember, these are rectangles because of of this approximation. There's no curvature because these circles are so close together. Well, the area of an individual. Let's start with this strip. So what's the area of this strip? So it's the circumference. Let's say the outer circle. It doesn't really matter because the circumference is basically the same from the inner and the outer. But let's say the outer circle. So it's the circumference. Remember, these are rectangles. Circumference multiplied by the circumference, which is of course the length of the rectangle, multiplied by the width of the rectangle, which is this tiny little sort of increment in the radius length. So I mean, you can see that the radius of this circle is slightly smaller than the radius of this circle. It's like an extra little increment between the two radii. So it's this tiny little difference between the two radiuses of the two circles that is the width. And this difference, of course, is tiny. It's infinitesimally small. So we're going to call it delta r. So the way to do it is to sum up all of these all of these individual circumferences times by all these little individual widths of each circle, widths of each strip, and then we're going to get the area. So because this is an infinite number of strips, and because the width of the strip is infinitely small, we've got a sum that's becoming an integral, a discrete sum that's becoming a continuous integral. So this delta r becomes a dr, and I've used a dash here because I want to actually I probably should use a dash here as well, but I've used a dash because I want to illustrate that it's the radius of each individual circle, not the radius of the big one that we're trying to calculate. So it's each individual one, and we're summing up of all of them. So incidentally, I've replaced the circumference of each individual strip, or the length of each individual strip, with 2 pi r, which of course we know as being the circle constant multiplied by the radius is the circumference. So we're summing up continuously this time because it's an integral over all of these radii, and we've got this little increment dr, and that's an integral. So when performing this integral, and the limit is, we start off in the middle, so that's obviously why we'll start off with 0 here. We'll start off with the radial distance from the centre as being 0, and we end up with the radial distance being r, and r is the radius of our big circle that we were trying to calculate the area of in the first place. So we integrate this, and it becomes this. R dash becomes r squared over 2. So 2 pi just stays as it is, and then you get this, and of course between the limits of r and 0, the radius of the big circle, and 0, this r dash evaluated is at r is r. So we've got 2 pi r squared over 2, which yields the familiar pi r squared. So these are sort of two methods you can do it. There are probably other methods. You could try and do it in a Cartesian coordinate system. I don't really know how to do a sort of intuitive geometrical version of that, but it gives me a headache just thinking about trying to do it in a sort of vertical or horizontal strip type of way. I don't know why anyone would punish themselves by actually doing that, but you could probably do it. And there are various other ways that you can sort of show what the area of a circle is. One particular method I've read about is by looking at polygons of increasing number of edges. So you start off with a triangle, then you go to a square, then you go to a pentagon, and so on. And of course, as the number of sides gets bigger and bigger, it's closer to a circle. Anyway, these two ways that you can intuitively, intuitively in the sense that if you don't know any calculus, you can still sort of see how this works, and then also the maths behind it. Calculate the area of a circle, show its pi r squared.